I'm Jeff Tabor. I'm the laboratory supervisor at the Impulse Manufacturing Laboratory at The Ohio State University. Today I'm going to talk a little bit about photonic Doppler velocimetry. It's an interesting technique for measuring the speed of objects. It was developed within the Department of Energy's national laboratories in the late 20th century, mostly at Lawrence Livermore National Lab and Los Alamos National Labs, and is attributed primarily to a guy named Ted Strand. All right, so what do we need the PDV for? Well, in our laboratory, we do impulse forming using a suite of techniques, all of which pretty much involve accelerating material to pretty high velocities in pretty short times. That's the nature of impulse. High peak powers, changes in energy during short periods of time. So to be quantitative about what we're doing, it's nice to have a diagnostic that can let us measure the velocity of the accelerated material. If we know that, we can take its derivative, find acceleration, integrate it, find its displacement. Having that kind of information, we can do things like solve force balance equation, say according to Newton's second law. If we know the acceleration of the material, the mass of the material that we accelerated, we can see what the force is. The force might correlate to the flow stress of the material and tell us other things like the efficiency of the process from the given input energy, how much force do we get acting on the material, and things like that. So for the science part of material science, it's important to be quantitative, and the PDV allows us to do this. So in all the methodologies that we use to create impulse and all the applications that we use, the PDV is quite helpful in getting a little more quantitative about the methodologies. So, as the name implies, photonic Doppler velocimetry, we're going to measure the velocity of a moving target using the Doppler effect. So what we do basically is we're going to shine some light from a stable laser source onto an object. Some of that light gets reflected, and there'll be, if the object is moving, the reflected light is a different frequency from that which we originally sent out to it. So the difference between the reference light and the shifted light is just the Doppler shift, and that represents the velocity of the target. So it's pretty simple. We're just going to mix or make a heterodyne from these two waveforms. And the output frequency of the heterodyne then represents the velocity of the target because it gives us the Doppler shift within it. So we can take a look at this schematically with a little more explanation. So light originates from the laser, and we couple this to some fiber and goes into a fiber optic device called a circulator. The circulator has, in this case, has 3 ports on it. What happens is the incoming light goes from port 1 to port 2. And everything that goes in 1 comes out 2, coupled again through fiber to a probe. Now the probe has a little bit of back reflection built into it, so a little bit of the laser light is sent back to the circulator. The rest goes out through the probe, through the lensing, strikes the target. Some of it that is reflected from the moving target is recollected and also mixes with the unshifted light, goes back into the circulator. Now the way the circulator works is everything that comes in port 2 goes around to port 3. So now we have the heterodyne output between the mixing of the unshifted light and the shifted light coming through the fiber to the photodetector. This makes a varying intensity signal to the photodetector, which changes the photocurrent, and gives us a varying electrical output from the detector to the data acquisition device, which in this case is an oscilloscope. We often sample at rates as high as 1 or 5 gigasamples per second, and it will acquire the time varying amplitude of the signal for us. So we can later take a look at the frequency of this signal and convert it to velocity. Alright, so the raw data from the oscilloscope is imported into MATLAB, and this is the a trace of the raw data. You can tell when the event begins. If we magnify in this area, you can see the change in frequency from DC to higher frequencies and even higher frequencies. That implies that the object is still accelerating. So using the MATLAB spectrogram command, we can take a Fourier transform of that raw data, looking at the frequency over a windowed sample, and plot that the highest power spectral density component in that window and assign a frequency to it. So now we've got a plot in the frequency domain. So you can see this is the acceleration here to there over time on the x-axis to frequency on the y-axis. So this point here is a frequency of 3 times 10 to the 8th, 300 megahertz.